Okay, young grasshoppers, this is it. This is the final lesson as far as derivative rules go. After this, you'll be able to pretty much take the derivative of anything. For all of these, we're going to assume that u is a differentiable function of x, and we're going to go through the exponential and logarithmic function rules now. So the first rule is the derivative of a constant a raised to a variable x, or a is raised to a function of x. So either way, it's the same idea. For all of these, the base, a, the constant, has to be greater than 0, and it can't equal 1. So when you take the derivative of a constant raised to a variable, it is just going to be the original problem, a to the u, times the derivative of the exponent. So we'll write that as du dx. And then times the natural log of the base. And that's it. So as you go through the derivative rules, or as you go through example 1, we're just going to follow that. So we've got a constant 4 being raised to a variable, so we're going to follow the rule. Dy dx, the derivative of y is dy dx, equals, it's the original problem, 4 to the 2x, times the derivative of the exponent, so that's just a 2, times the natural log of the base, which is 4. Okay? There is nothing you can do to simplify this other than maybe putting 2 times the natural log of 4 times 4 to the 2x. But this 4 is being raised to the 2x, so you can't multiply this 4 with this 2 and make it 8 to the 2x. It doesn't work like that. Order of operations still prevails. But that's it for example 1. And we'll go on to the next page. For example 2, it's asking us to find out what point on the graph of the function y equals 2 to the x minus 3 does the tangent line have a slope of 21. Okay, so tangent means derivative. Slope being 21 is going to be something that we're going to plug in. So the derivative of y is dy dx. Over here, I've got a constant raised to a variable. So I'm going to follow the derivative rule from the previous page where it's the original problem times the derivative of the exponent, which is going to be 1, times the natural log of the base. So that's just the natural log of 2. And the derivative of this minus 3 part over here goes to 0. It's a constant. So that's the derivative. That tells us the slope for anywhere of the function y. But we're asking for at what point on the graph does the function have a slope of 21. So at this point, we're going to plug 21 in, and we'll have 2 to the x times the natural log of 2. And now it's all algebra. We're trying to solve for the variable x. So the first thing I'm going to do is divide both sides by the natural log of 2. I'll have 21 divided by the natural log of 2 equals 2 to the x. And in order to get that x out of the exponent, you can take the natural log of both sides. So the natural log of that stuff and the natural log of that stuff. And what that allows us to do, if you remember your derivative or your exponent rules and logarithm rules, any exponent and the argument of a logarithm can drop down to the front. So that's going to allow us to say the natural log of the left-hand side, we've got 21 divided by the natural log of 2, is going to equal x times the natural log of 2. It's not pretty. I never said it would be. We're going to divide both sides by the natural log of 2 now. We'll have the natural log of 21 divided by the natural log of 2. And all that is divided by the natural log of 2. So when x equals that mess, you're going to have a slope of 21. All right. Example 3 is asking you to find the derivative of y equals e to the x. So again, e is a number. It's the natural, this is a natural base e. And we're going to follow the derivative rule because it's a constant being raised to a variable. So dy dx equals the original problem, e to the x, times the derivative of the exponent, which is 1, times the natural log of the base. And at this point, we bring in something that you guys should have learned in algebra. Okay, the natural log of e is just 1. So at this point, we get to something kind of interesting here. The derivative of e to the x is e to the x. Okay, so the exponential function e to the x is special because the derivative is the function itself. So we can take this and apply it one step further and make that a special rule so that if we take the derivative of e to the u, it's just going to be e to the u times the derivative of that exponent. Okay, so that natural log of the base goes away because the natural log of e is just 1. All right, so let's take it and do something with it here. Let's take a look at example 4. We've got y equals 3 times e to the 2x. So the derivative of y is dy dx. And for this particular problem, this is a constant multiple of 3. And we've got e to the 2x. So it's a constant to a variable. So you rewrite the original times the derivative of the exponent. And again, times the natural log of the base, but the natural log of e is just 1. This can be cleaned up. 6e to the 2x. Okay. Right now I'd like you to hit pause and try example 5 on your own and then come on back. You didn't try it on your own. Hit pause and really go do it this time. All right. dy dx, the derivative, equals e to the cosine of x times the derivative of that exponent, which is negative sine of x. This would probably just be rewritten so that the negative, you know, I've seen it written both ways, where it's the sine comes first, or they leave it as e to the cosine x times the sine of x, and then they just put the negative out front. So it's all the same thing. That commutative property of multiplication lets you kind of do anything you want with it. But any of those answers would be acceptable. Okay? So anytime you have a constant raised to a variable, that's the rule you're going to follow.